Good morning, guys. Today's notes are going to be on the wave speed equation. We're going to be talking about how fast waves travel from one location to another. Here we go. So I have an ocean wave, and this ocean wave is going to go that way. All right. I'm going to call that speed that it travels v. And of course, we all know from the very first equation ever in physics that speed equals distance divided by time. It's how far the wave goes divided by the amount of time it takes. And that's it. That is the wave speed equation. Or is it? Well, yeah, it is, but it isn't because there's some funky letters here. We have v, which is fine. That's the wave speed. But what are these f and these lambda Greek letters? Yeah, so it turns out this v equals distance divided by time equation. Hold on, I didn't like the circling. Better circling. Is actually the same thing as v equals frequency times wavelength. And I'll show you that here in a second. But here we go. Wave speed is how fast the wave pulse travels. All right, this is not the same thing as frequency. Frequency is how fast a wave particle shakes back and forth. But this is how fast a wave pulse travels, and it's just speed equals distance divided by time. And if that's true, it's measured in meters per second. It does not depend on how fast you're shaking the slinky. It doesn't depend on how wildly you're shaking the slinky. It turns out that if you make a pulse in a slinky or if you make a pulse in a medium, it will always travel the same speed. So, regardless of how you made that pulse. So, the wave speed doesn't depend on frequency of the shaking, and it also does not depend on the amplitude. It depends on the medium itself, what the wave is traveling through. What does that mean? Well, things like air. We know sound is a wave that travels through air. Does sound ever travel faster through air than in certain air than in other air? The answer is yes. It turns out sound travels faster in hotter air, and sound also travels faster in denser air. But it doesn't matter how loud you yell. That does not affect how fast it will take, how long it will take for the echo to go out and then come back. It only depends on the temperature of the air and the pressure of the air. So the medium itself, the air itself. All right. Now, it turns out we can use this wave speed equation if we know the speed in meters per second and we know the frequency of the oscillation. We can figure out the wavelength of the oscillation. Alternatively, if you know the speed and the wavelength, you can figure out what frequency that sound must have been. Okay, but first we're going to do a basic one. We're going to use what is the speed of this wave, and we're going to say, hey, it took 2 seconds for this many oscillations. Let me count the oscillations. 1, 2.5 oscillations. It took 2 seconds, and it traveled 4 meters in that time. Well, okay. Wait a second. That's not right. 2 seconds. That's a capital T, not a lowercase t. This is a period. That's the period of time for 1 oscillation, not for 2.5 oscillations. I can't use distance divided by time, or can I? No, that's complicated. Let's do this instead. I'm going to say the period is 2 seconds, which means the frequency is 1/2 of a hertz. And what's the wavelength? C. The total length is 4 meters, but there are 2.5 waves, so the wavelength is equal to the total distance, or the total length, divided by the number of waves. So the wavelength, that's lambda, Greek letter lambda, is 4 meters in 2.5 waves, or, let's see, 4 divided by 2.5. 4 divided by 2.5. That means each wave must be, let me pull out my calculator here, 4 divided by 2.5. Each wave is 1.6 meters long. So the wavelength is 1.6 meters. Oh, here we go. Here we go. Lambda equals 1.6 meters. F equals 1/2 hertz. That means the wave must have traveled at a speed of 1/2 hertz times 1.6 meters, or a speed of 0.8 meters per second. According to that, V equals frequency times wavelength equation. Okay, that's great. Now there's actually another way to do this. You probably looked at this and said, hey, what about distance divided by time? Speed equals distance divided by time. Let's see. Total distance was 4 meters. Total time, let's see, total time. Time for one oscillation was 2 seconds, but there were 2.5 of those, so let's see, one oscillation's 2 seconds, 4 seconds, and a half is 5 seconds. So 4 meters in 5 seconds. So the speed would be 0.8 meters per second. Woohoo! It checks out. That means that speed equals distance divided by time. This equation is the same thing, gives you the same answer, as speed equals frequency times wavelength. Huh, well that's cool. All right, that means you can use either equation if you understand how to use it. But in the equation on the left, I used, over here, I took one oscillation, or one wave, and over here I did all the wave pulses. In other words, 2.5 of them. All right. So there's two different ways to do this problem, and sometimes it's easier to do one way, sometimes it's easier to do the other way. But just keep in mind, do you want to do it with a one wave pulse, in which case you're using 2 seconds and 0.8 meters, or 1.6 meters? Or do you want to do it with all wave pulses, in which case you're using 5 seconds and 4 meters? Gives you the same answer either way. All right, problem 2. An observant pelican notices 4 wavecrests pass by her post every 3 seconds. 4 wave pulses every 3 seconds. 4 wave pulses. Wait, that's not what's shown in the picture. Or is it? No, actually the picture doesn't tell you the number of wave pulses per second. The picture shows you the number of waves in between the posts. Those are two different things. So the frequency is 4 waves in 3 seconds. And of course, we all know that is 1.33 hertz. Now this picture says how many waves? How many waves is this? So I'm going to start at a crest and go down to the bottom, back up, that's 1 wave. Down to the bottom, back up, that's 2 waves. 2 waves in 6 meters, so that means a wavelength is 3 meters for 1 wave. Okay, that means the wave speed, frequency times wavelength. So wave speed is 1.33 hertz times 3 meters, which is 4 meters per second. And that's how fast those waves must be traveling to make those two waves. Okay, last one, problem 3. EM spectrum. EM spectrum is light. It's also radio waves and microwaves and gamma rays and X-rays and infrared and ultraviolet. Yeah, you may already know that from chemistry, but we are actually going to do some wave speed calculations with that. It turns out that, did you know that the speed of light is a thing? It's not infinity. It's it's that. What is that? Is that a big number, little number? That is a massively huge number. We call speed of light is 300 million meters per second. It is so fast that it has its special name. We call it c, which is actually Latin for celeritas, which means speed or quickness. But anyway, it is the fastest thing ever. Speed of light is nothing can go faster than the speed of light. You probably already know that. But speed of light, and it's asking for what's the wavelength of B96. B96 is a radio station here in Chicago. It broadcasts at a frequency of 96.3 megahertz. Coming at you from 96.3 megahertz. This is B96. All right, here we go. 96.3 megahertz, that means its frequency of the light coming from the radio station, it's actually radio waves, but is 96,300,000 hertz. So the question, of course, is what's the wavelength? How long is it between these electromagnetic wobbles? Well, that's pretty easy. V equals frequency times wavelength. So 300 million equals 96.3 million times the wavelength. And my calculator says, let's see, 300 million divided by 96.3 million. That gives me a wavelength of the B96 radio waves of 3.1 meters. That means, among other things, that if you're going to make a B96 radio station antenna, you're best served with an antenna that is approximately 3.1 meters long, or about 10 feet long. Or is that 11 feet? That's about 10 feet. About 10 feet long. Is that reasonable for a big radio station antenna? Yep, I think so. All right, great. That's it. That's all for today.